Hello, problem solvers. This is lesson 16, our last one before Easter break. And we're going to talk about polynomials now that we've done functions. We've done all kinds of algebra and sums and products, and now we're going to tackle polynomials, our favorite functions. Polynomial is a mathematical expression, not an equation, involving a sum of powers of variables multiplied by coefficients. And here you have coefficients of x and powers of x. You could have multiple variables, and it would still be a polynomial. Each individual summand from each term, those are called monomials. If you had two terms, it's a binomial. That's where we get the binomial theorem and so on. The degree of a polynomial is the highest exponent with non-zero coefficient. And keep in mind, we want integer powers right now. This coefficient is also called the leading coefficient. If the coefficient's 1, we call that a monic polynomial. And if you think about limits in Calc 2 or Calc 1 and things like that, we often care about the leading coefficient. It also helps for factoring things like that. Addition works the way you want. You add term by term, you subtract term by term. Multiplication is complicated. You do FOILing there. There's a thing on the bottom about division. It's kind of a convoluted way to write it. Also, I don't see the original that they want there. So kind of don't worry too much about that expression, but think about long division that you did in Calculus 2. All of you guys in class are in, at least in Calculus 2, and we did long division when we did partial fractions, and so that's really what we need to focus on. So you can kind of ignore that example. Just remember, really here they're saying x cubed plus x plus 1 divide by divisor x plus 1. So if you write that out with partial fractions, you'll see that, and then if you get rid of the denominator when you would do a partial fraction, you'll get that expression there. So you might pause the video and try to multiply that out and see if that makes sense to you. Division algorithm is a trick for kind of doing what we just saw there. If you have two polynomials, and so they said this big F they're saying is the integer. So basically they just mean you have polynomials with integer coefficients, and that the second polynomial is not 0. Then you're going to be able to kind of do a division thing here. If you look at g of x, q of x, basically q of x is the quotient, and then r of x is the remainder. So this is, again, basically kind of long division, but they've multiplied it out so that you don't see a fraction anymore. And so there's an algorithm for doing this. And the remainder theorem is an application of the division algorithm. When you divide by a linear term, then the remainder will be a constant. And that's part of how we did partial fractions in Calc 2, was that when you were setting out partial fractions, you knew when you divided by a linear term, you would get a constant at the end. And that constant, if you plug a into this expression, you get f of a on one side, and you just get r on the other side. The factor theorem, what it means to have a root. If you plug in a number and you get 0, then you have a linear factor. That means that x minus that number is a factor of the polynomial. By the way, before I go too far, the division algorithm isn't listed out there. I would normally write that out, and I might make a separate video where I do that if you guys request that. But if you open Zeitz, your problem-solving book, and go to this section, which I think is chapter 5, I don't remember which section, 5.4 maybe, they work out the division algorithm. And if you guys aren't following that, I can make a video of showing how to do that. The fundamental theorem of algebra states that every non-constant polynomial with complex coefficients has at least one complex root. Remember that complex roots include real roots, right? So every non-zero polynomial has exactly as many complex roots as its degree, and each root is counted up to multiplicity. This is a complicated sentence, but what it's saying is if you include imaginary numbers, every polynomial completely factors. That's what they're really trying to say. Now, if you want rational roots, so not only real but rational roots, that's an extra constraint on polynomial equation with integer coefficients. So all those ANs are integers. If you take the first term and the last term, if those are not 0 and they're integers, then if you're hunting for rational solutions, they would have to be this. You'd have to have the top of the rational root be an integer factor of the constant, and the bottom has to be an integer factor of the leading term. So you can check if you just factor the constant and you factor the leading coefficient and kind of just take different versions of the factor of the constant over a factor of the leading coefficient. Those are the only possible rational roots.